This is the fourth section of chapter 7, and this section is on the difference between the means of two independent normal distributions. So what we'll be doing in this section is working out what we call a pooled estimate for the population variance, sigma squared. And what we'll also be doing is we'll be using this pooled estimate that we've just worked out to calculate a confidence interval for the difference between two means. And then in the next section we'll be going on and doing a hypothesis test for this difference between two means to show if there is actually a significant difference between two sample means, and then using this to see if that shows that there's a difference between two population means. So let's first of all start with random samples from two different populations where we have the following three features. Both populations are normally distributed. The samples are independent of each other, so the samples that I take within each population and from each population are independent of each other, and the variances of both populations are the same, or we're assuming that the variances of both populations are the same. So if I have a certain number of samples from one population, population X, and another set of independent random samples, so these independent random samples as well, from population Y, then an unbiased estimator for the variance of population X is going to be this formula. We're used to seeing that, we've seen that before. And then an unbiased estimator for the variance of population Y will be this, so it's the same formula up here, just with Y's in it. Then if we want to work out a pooled estimate for the population variance of both of these populations, we're assuming that the variance of both populations are the same when we're trying to work out what that is. That will be this, so SP for pooled squared, so variance, and it's N, basically the number of samples in population X, my first sample, minus 1, times by my unbiased estimator for population X. So you can see that if I highlight it, this comes from doing this calculation here. You can see why we didn't stick it all in one formula. It would look too complex. And then we add to that the number of samples in my second population, minus 1, times by the unbiased estimator for population Y, so that comes from here. So again, all of this calculation needs to be done, and then that goes into the formula, and then that all gets divided by the number of samples in both populations added together, take away 2. That's basically the same as n sub x minus 1 plus n sub y minus 1. We put it together and we get this at the bottom here. So we've looked at how to work out this pooled estimate part, pooled estimate for the variance. Let's now look at how we can use this here to find a confidence interval for the difference between two means. So looking at this, the confidence interval, the confidence limits for the difference between two means, it's given by this formula here. So it's the mean of population X, so that's how we get this value here. Then the mean, or the sample mean of population Y, so that's where we get this value. Then it's plus or minus, so this will give us the upper confidence limit by adding the lower confidence limit by subtracting T sub C. Now this is the T distribution with C degrees of freedom, and C we get from doing the number of samples in X plus the number of samples in Y minus 2. Now you'll notice that's the same as this value here. So maybe if I highlight that so that you can see that these two values are the same, that's going to be the same as the value that goes there. Then that gets times by the square root of the pooled variance. So actually we need to work this out first, square root it, and that goes here, and then that gets times by the square root of 1 over the number of samples in population X plus 1 over the number of samples in population Y. So if we look at that on a diagram, then the width of this bar here is our confidence interval, and our lower confidence limit is going to be this value here, and our upper confidence limit is going to be what we get from working out this value here. And just one last thing, and that is when we have our two samples and we work out the mean of each sample, we want this to be the larger mean of the two samples that we take. So this value should be the largest sample mean. So we're going to have to work out the means first before we decide which is population X and which is population Y. Doing it that way round just avoids getting a negative here. We always want this to be positive. So work out the means of each of your samples first. The one that has the largest mean, that's what you make X here, and choose for X here. And when you work out the variance of X here as well. Example 10. A random sample of 15 observations is taken from a population and gives an unbiased estimate for the population variance of 9.47. So the sample of 15 observations, that has a variance of 9.47. A second random sample of 12 observations is taken from a different population and has the same population variance as the first population and gives an unbiased estimate for the variance as 13.84. So 12 observations has a variance of 13.84. Calculate an unbiased estimate of the population variance sigma squared using both samples. So assuming both populations are normally distributed and the samples are independent, then we can use this formula here. Now we're told that both populations have the same variance, so we don't need to assume that. But once all three of those conditions are met, two of them is already given, one is already given, two of them are assuming, then we can use this formula here. So we'll just go through and write down what these different values are. So the number of samples from population X, we'll make that my first one, is 15. The population variance, or unbiased estimate for the population variance of that population is 9.47. The number of samples from the second population is 12. And an unbiased estimate for that variance is 13.84. So all we need to do now is put those formulas or numbers into the formula. So it's going to be 15 minus 1 times by 9.47 plus, then it's going to be 12 minus 1 times by 13.84, all divided by 15 plus 12 minus 2. And that gives me exactly 11.3928. Now I guess I could round that to 3 significant figures, or maybe 2 decimal places, since these look like they've been rounded to 2 decimal places. These could be exact values, by the way, I don't know. So since it's not a big long decimal, I won't round it, I'll just write the full answer down for that one. Okay, so this is my pooled estimate. So that's the technical term, the proper name, pooled estimate for the population variance. So these two populations, we're saying this is our estimate for what the variance of these two populations are, we'd really want a confidence interval rather than a single value. So that's what the next example is going to deal with. Example 11. In a survey on the petrol consumption of cars, a random sample of 12 cars with 2-litre engines was compared with a random sample of 15 cars with 1.6-litre engines. The following results show the consumption in suitable units of the cars. So here they are, the 2-litre cars, and here this is my sample of 12 cars. So I'll just write that in brackets there, I've got 12. And for the 1.6 litre, it says that that's 15 cars. So I'll just put 15 here. Calculate a 95% confidence interval for the difference between the two mean petrol consumption figures. You may assume that the variables are normally distributed and that they have the same variance. And we're also assuming that these samples are independent as well. So here's a reminder of the formula that we need to use. Now remember, the population that we choose, that we're going to call population X, needs to be one with the larger mean, because we don't want this to be a negative. So before we start deciding, right, the first one is X and the second one is Y, we need to work out the mean of these, and while we're at it, we might as well then work out the variances. And the easiest way to do that is to use our calculators. Right, so I've put these in, but I need to look at the means first. So the mean of the first list is 30.933, and it seems to be recurring. And the second one is 37.04. Now in the CG50 this is quite easy, because basically I've typed in this set of numbers as list 1, this set of numbers as list 2, and then you can easily flick between the two. So I can see that because this one has the larger mean, and I want the larger mean there, it's going to be the second list that's going to be the X in my calculation, and the first list, which is going to be the Y in my calculation. So I can now go back in and fill these numbers in. So my X population on my sample for my 1.6 litre cars has 15 in its sample size. The mean is 37.04, which we worked out here, and then the unbiased estimator for the X population is this 2.62564, and then I think it's 277 after that. Now we'll fill it in for Y. So number of my Y samples 12. The mean of Y, the 2 litre cars, 30.9333, looks like the 3 is recurring, and its variance 2.85954, and then I think it's like 0.11 after that. We need to work out the degrees of freedom for the T distribution. Now remember, the way that we work out T is we're going to add together the number of our X, the number of our Y, minus 2. So it's going to be 15 plus 12 minus 2, and that gives us 25 degrees of freedom. Now we'll look up this T value. Now since it says it's a 95% confidence interval, and it's a difference between the means, and we have a positive and a negative value, this is like two-tailed, because we're going to have two values, a positive and negative. So this will be a two-tail test, which means that I'm going to be looking for the 2.5% value, and that's 2.060, 25, row 75, 25, yeah, 2.060. So now all we need to do is plug all those values into the calculation. So 37.04 minus 30.933, and I'll put recurring there. Actually, let me put in what I'm going to type in on my calculator. So since the table here value is 3 decimal places, I want to do at least 4 decimal places in my working, I can use more, plus or minus, and then it's going to be this t value 2.060 times by, now we need to work out the pooled variance. Okay, so that's going to be the number in sample x minus 1, so I'll write the whole thing out, so 15 minus 1 times by the variance of my x population, so it's going to be that number squared, so 2.6256 squared, and then we add to that ny minus 1, so 12 minus 1 times by the variance of y, so that's going to be 2.8595 squared, and then all of that needs to be divided by n sub x 15 plus n sub y 12 minus 2. So this gives me 7.45849. Okay, so what I'll do, that needs to be square rooted, so that'll be square root of that, 7.45849, and that's going to get times by the square root of 1 over 15 plus 1 over 12. Right, so we're going to get the first value here, so this 6.1066 number, which came from here, plus or minus, so plus or minus what we get from doing this part of the calculation, so this part here, all of that gave us this number. So we'll clear some space so that we can write down what those two values are, and then from that we can write down what the actual confidence interval is. So these are the values to 3 decimal places. You could also give 3 significant figures as well. So my final confidence limit is here. Now basically what this means is if we're working out the difference between these two means, we can be 95% confident that the difference between these two means will lie between these values. And we'll say, if we're testing at 95%, we'll say that's acceptable if the difference lies between these two values. If the difference is outside of these ranges, then I may suspect that the means are not, the difference is too great, so that moves on to the next bit, the next section, which is all to do with hypothesis testing. But for now, that's just the confidence interval there. So you should now be able to do exercise 70 on pages 183 to 184 of the textbook.